Hey everyone, and welcome to today's Explainer. Think of this session as your very own professional university lecture, designed to take you deep into the core of software engineering. Now, have you ever wondered why software engineers don't just build every new system from scratch? Or how massive companies like Visa manage to process over 20,000 transactions a single second without a total system meltdown? Well, today we're going to answer exactly that by exploring application architectures, and then we'll wrap things up with a comprehensive summary of our entire architectural design chapter. Let's dive right in. Here is our roadmap for today. We'll start with an introduction to application architectures, move into transaction processing, cover information systems, explore language processing, run through our Chapter 6 summary, and finally wrap up with an exam-focused checklist.
All right, let's kick things off with Section 1, Introduction to Application Architectures.
So, application systems are basically built to meet a specific business or organizational need. And here's the thing, businesses operating in the same sector usually need the exact same basic software. For instance, all banks need account management systems, right? And all universities need student registration systems. Because of these huge commonalities, software engineers use generic application architectures that capture the core characteristics of these systems. But why use a generic architecture in the first place? Well, think about the massive headache of managing a complex team and the sheer inefficiency of building completely new systems from the ground up every single time. It just makes sense to use a standard, tried-and-tested structure that you can easily configure and adapt.
As a software designer, you can actually use these generic models in 5 really practical ways. First, they act as a fantastic starting point for your design process. Second, you can use them as a design checklist to make sure your own architecture is structurally sound. Third, they are great for organizing team development. Because architectures highlight stable structural features, you can assign different groups to build different components all at the same time. Fourth, they give you a way to assess components for reuse. And fifth, they provide a shared vocabulary so you and your team are always speaking the same language.
Moving right along to Section 2, Transaction Processing Systems. Now, transaction processing systems are the absolute backbone of almost all interactive business systems, from banking to online shopping. But to really understand them, we need to lock down a fundamental technical term, the database transaction. A transaction is a sequence of operations that is treated as a single atomic unit. And atomic simply means all or nothing. Every single operation in the transaction has to be completed before any database changes are made permanent. Now, here's a really common misconception. A lot of students think atomic means it happens instantly. It doesn't. It just means that if even one tiny step fails along the way, the entire sequence gets rolled back. That is absolutely crucial to make sure inconsistencies don't corrupt the database. Let's make this concrete with something we do all the time: withdrawing money from an ATM. This transaction involves 3 very distinct steps. First, the system checks your account balance to see if you actually have the funds. Second, it updates your account balance by subtracting the withdrawal amount. And third, it tells the ATM to physically dispense the cash. Until all 3 of those steps successfully complete, the transaction is unfinished, and the bank's database remains completely unchanged. When you architect an ATM system like that, the transaction processing is generally organized using a pipe and filter architecture. Think of it like an assembly line. On the input end, you grab the customer ID and validate their card. That data flows right into the processing component, which queries and updates the account on the bank's database server. Finally, the results flow out to the output component, which prints your receipt and dispenses your cash. Input, process, output. Very clean, very linear. Let's transition to Section 3, Information Systems Architecture. Think about a university library catalog, a flight timetable, or a massive e-commerce website. These are information systems. Their job is to allow controlled access to a huge base of information. And guess what? Underneath the hood, they are essentially just transaction processing systems built using a layered approach. At the top, you have the user interface layer, usually running in your web browser. Right below that is user communications, handling things like logging in and authentication. Then we drop down to the information retrieval and modification layer. That's where the specific logic of the application lives. And at the foundational level, we have the database and transaction management layer. Now, in modern distributed internet systems, these logical layers actually map directly onto physical servers in what we call a multi-tiered client-server architecture. The user interface and communications run on a web server. The core logic runs on a dedicated application server, and the heavy lifting for transactions happens on a database server. Be careful here, though. A really common mistake students make is totally confusing the logical layers with the physical servers. Remember, multiple logical layers can run on just one physical machine, but separating them out physically allows for incredible throughput, letting systems handle thousands of operations a minute.
Next up, Section 4, Language Processing Systems.
If you have ever written and compiled a Java program, you've used a language processing system. It's pretty amazing. These systems take your intentions, written in a formal language like Java or Python source code, translate them into a specialized internal format, and then execute them. So your source language instructions come in, a translator verifies the syntax and semantics, and then it generates instructions for an abstract machine. Finally, an interpreter fetches and executes those abstract instructions to give you your final output.
When we look closely at programming language compilers, they follow a very strict pipeline. First up, a lexical analyzer takes your code and breaks it down into internal tokens. Next, a syntax analyzer checks your grammar and builds an internal representation, usually something called a syntax tree. Then, a semantic analyzer takes that tree and makes sure the code actually makes logical sense. Finally, a code generator walks through that tree and pumps out the abstract machine code.
But things change when a language processing system is built into a programming tool, like the Interactive Development Environment, or IDE, that you code in every day. Instead of a straight, one-way pipeline, all of those analyzers and generators are clustered around a central shared repository. They all communicate by constantly accessing a central symbol table and syntax tree.
So the big takeaway here is knowing when to use which pattern. A pipe and filter pattern is brilliant for sequential batch processing. That's when you just hit compile, sit back, and wait for the output. But if you're building an IDE, you absolutely need a repository pattern. Why? Because an IDE needs to be real-time. As you are typing away, your editor needs immediate, shared access to that repository, so it can highlight your syntax errors instantly.
All right, let's zoom out now for Section 5, our Chapter 6 summary.
It's time to recap everything we've learned in Chapter 6. First, remember that software architecture is never just one single diagram. It's documented from multiple distinct perspectives or views. We have the conceptual view, logical view, process view, development view, and physical view. And keep in mind, when you are designing, your non-functional requirements will almost always conflict. Building a system for maximum blazing fast performance might completely conflict with making it easy to maintain later. Good architecture is all about intelligently balancing those trade-offs.
We also covered 5 core architectural patterns. These are your reusable templates for organizing a system. We explored Model View Controller for user interfaces, the layered architecture to keep concerns separate, the repository pattern for shared data, client-server for distributed systems, and the pipe and filter pattern for data processing. These patterns are literally the building blocks of all the application architectures we've talked about today. And finally, Section 6, Exam Focus and Conclusion. Listen up, because this is your dedicated study checklist for the exam. You must know these 3 things cold. Number 1, be able to explicitly define an atomic transaction as an all-or-nothing sequence of operations. Number 2, list the 4 distinct layers of a generic information system architecture: user interface, user communications, information retrieval, and database. And number 3, perfectly outline the language processing pipeline, starting from the lexical analyzer all the way down to the code generator. And with that, huge congratulations, you have officially mastered Chapter 6 on architectural design. You now deeply understand that architecture is the fundamental backbone of any software system, and you are totally ready to tackle detailed design and implementation. Before you close your notes, I'll leave you with this thought. When you are the lead software engineer on your very first real-world project, which of these architectural choices will you use to define your system? Thanks so much for joining me for this explainer, and happy studying!